that over here, the cable AB diameter is 25 millimeters, right? To support, and then we know that over here, this structure over here is a square, right? And is 100 millimeter by 100 millimeter. So the square bar BC is made of steel, okay? And then we are given that the yield is at 300 megapascal. And then the Young's modulus is at 200 times 10 to the power 9 gigapascal. Okay. And then the high strength steel, the cable, AC is the cable. We know that the yield is equal to 1800 megapascal. Okay. And the Young's modulus is equal to 190 gigapascal. So determine whether the structure can support a load of 200 kilonewton as shown. And we only consider in-plane buckling only, okay? And use a safety factor for 2 for the Euler's buckling, right? And the safety factor for yielding of steel is 1.5. Okay, so we are given a safety factor. So determine the structure can support. So can the structure support the 250 kilonewton? Okay. So now we have all those information, right? We're going to see is a structure able to support. So I know, yeah. So the structure is going to fail. It's possible to fail in 2 ways. Is it going to fail in buckling, or is it going to fail by the maximum stress that we calculate is greater than the yielding, and then the structure will fail. In this case, the failure is when the loading goes from elastic to plastic. That's how I consider failing. Okay, so that's how I look at failing. Right. So let's start. So we know that the area. So we're going to calculate the area first. Okay. So the area of BC. So BC for this case is the square section, the structure, right? So this is equal to 0.1 times by 0.1. So this is 10 times 10 to the power minus 3 meters squared. Okay, we know that. And then we are going to calculate the area, cable, area, AC. So this is equal to AAC. So this is equal to pi. So the diameter is what? Given the diameter is equal to 25. So it's 12.5 radius. Right? So this is equal to 480.874 times 10 to the power minus 6 meters squared. Okay, so you have your area now. So we are given the factor of safety for buckling, okay, is equal to 2.0, right? So use a factor of safety for Euler's buckling, 2.0, right? And then the factor of safety for non-buckling is going to be at 1.5. Okay. So first thing of all, we will analyze the structure, right? So we are going to perform truss analysis. Okay, we are going to perform so most of you have done your 2P04 one way or the other. So what do we mean by truss analysis? Anyone? When we highlight, hey, we're going to carry out the analysis based on truss analysis, what do we actually mean? Anyone? Can you all remember? Anyone, please? No, none of you remember. It's okay. So when we say perform truss analysis, we are only going to consider axial loading only. Okay, we are only going to consider axial loading. We're not going to consider bending or whatsoever. Okay. So for this case, we're going to apply method of joints. I hope you all remember your method of joints. All right. If not, I can do a very quick. At point C, okay, to find the axial forces for members AC and BC. Okay, so I'm going to draw a point. So this is a point down here, and this point is known as our point C, and then we have a load coming down, which is 250 times 10 to the power 3 Newton. Okay, so this is given in the question. Then I'm going to draw my neutral axis. So the green is the neutral axis, and they're the neutral axis. So this neutral axis, the one that's in a gradient, is for member AC, and the other one is for member BC. Okay. So to apply member, so now if you look at C, right, due to the 250 Newton, the point C is going to come down. Okay. And because this is truss analysis, right, the forces have to be drawn, have to be parallel to the neutral axis. So all these are all our neutral axis, right? So the only member over here that can withstand a vertical load is member AC, right? So we know now, right, over here, this is known as our ACY, okay? The ACY have to be pushing upwards to counter the downwards of 250 times 10 to the power 3, right? So as I said, this is a truss analysis. All the forces must be parallel to the what? To the neutral axis. So for this case, we are going to have a ACX over here, right? So we know that we have a force down here, which is acting exactly on the neutral axis, and this is known as our FAC. Okay. Now, the problem now is what? We have a what? ACX. Okay. So now ACY is supporting is preventing the 250 from coming down, but we inherit a problem known as ACX. Right? Why we have to have ACX? Because FAC, we need to have the force that's applying parallel to the neutral axis. Right? So now you have ACX going towards the left. Right? Now we have to counter it. And this is known as your BCX. And BCX happen to be also equal to your FAB. Okay? So now we have resolved the forces from point C, but we still need to find how are the forces acting on member AC. Okay, so now this is member AC. Okay, so this is your member AC, and this is your member BC. And then we apply Newton's third law. Action is equal to reaction, same direction, different, sorry, same magnitude, different direction. So now this is your FAC, and Newton's third law, action equal to reaction, same magnitude and different direction. So now this is your FBC. I got it wrong down here. Why do I write FAB? Okay. Right. So what we discover down here is this is tension, and over here this is compression. Okay. So before we do anything, let's do our static analysis first. Okay. So we're going to perform static analysis. Summation about forces in the y direction is equal to 0, right? So you have ACY minus by 250 times 10 to the power 3 is equal to 0. So ACY is equal to 250 times 10 to the power 3 Newton. Okay, that is your ACY. So we want to find what is our ACX, right? We want to find our ACX. So we use similar triangles. So ACX, okay, ACX over 4 is equal to ACY over 3. Why that's the case? Because if you look at the geometry, right? If you look at geometry, right? The distance from here to here, this is in a question, okay? This is 4 meters, and this is 3 meters, okay? The forces likewise, okay? The forces will go that this is your ACY, ACX, and we just use similar triangles, FAC, okay? Right? You can calculate the angle, so you can use this angle and calculate the answer will be the what? Will be the same. So ACX now will be equal to 4 over 3 ACY. So this will be equal to 4 over 3 multiplied by 250 times 10 to the power 3. Okay. So this will give you 333.33 times 10 to the power 3 Newton. Okay. So this is your ACX. So you can calculate your FAC now. Equal to 250 times 10 to the power 3 squared plus by 333.33 times 10 to the power 3, okay, times 10 to the power 3 squared. So your FAC over here will be equal to 416.667 times 10 to the power 3 Newton. Okay. Then we find our FBC is equal to, in fact, we have our FBC already. FBC is going to counter ACX, right? So ACX, so FBC is going to be equal to 333.33 times 10 to the power 3 Newton. Right. So we have these numbers now. Okay. So now, how are we going to analyze the structure from here on? Okay. So let's look at, now I'm going to ask you a question. Which member will fail by buckling? Anyone? AC
BC.
or BC? BC. Why do you say that?
Because you have compression, FBC.
Well, that's the answer. Remember when we started, what did we say? When we started, right? We started by saying the structure is under compression loading, right? Then we have to consider what? Buckling. If it's tension, forget it. So that's why it's so confusing in this question. Okay, that's why it's so confusing. Where if we don't understand the